In this section, we're going to talk about a probability distribution called the binomial probability distribution. Freeze the video here and just read this little blurb here that kind of explains the difference between discrete and continuous random variables. We're going to focus on two types of random variables in this chapter, and one is a discrete random variable, which is the binomial probability distribution. And then the next section we'll talk about a continuous random variable, which is the normal distribution. Now, before we talk about a binomial distribution, let's talk about what a Bernoulli trial is. If we were to toss a coin, we could say either a head or a tails occur. Or we might phrase that a head occurs or a head doesn't occur. If we roll a die, we could say either a 3 occurs or it does not occur. If we draw a card from a deck, we could say we get a face card or we don't get a face card. If you take a medicine, you could say it eliminates the symptom or it does not eliminate the symptom. All of these have one thing in common. They have only two possible outcomes. So anytime you're performing an experiment where there's only two possible outcomes, then we more than likely can refer to that as a Bernoulli trial. So those three, you either get a head or no head, a 3 or no 3, a face card or no face card, or eliminate the symptom or don't eliminate the symptom. So these are called Bernoulli trial. They're named for a guy named Jacob Bernoulli. Now, a Bernoulli trial is an experiment where only one of two possible outcomes will occur. One outcome is associated with success, and the other outcome is associated with failure. The probability of success we'll call small p, and the probability of failure we will say is small q. Please keep in mind that success and failure depends on who's performing the experiments. If a basketball player is shooting a free throw, is success making the shot or missing the shot? Well, that would depend on which side you're on. So technically it depends on what you want to define success to be. Now, the probability of success plus the probability of failure in a Bernoulli trial must equal 1. So P plus Q would have to equal 1, which means that P is 1 minus Q, or Q is 1 minus P. So here's an example. If we toss that coin and success is getting a head, then P would be 1/2, and Q getting a tail or not a head would be 1 minus 1/2, which is also a half. If we roll a die and say success is rolling a 3, then P would be 1/6, and Q, which would be failure not rolling 3, would be 1 minus 1/6, so that probability would be 5/6. If a card is drawn from a standard deck, if success is selecting a face card, then P would be 12 out of 52, which is 3/13, and failure, not drawing a face card, would be 1 minus 3/13, which would be 10/13. Okay, so what are the properties of a Bernoulli trial? You must have only two possible outcomes. Each outcome has a fixed probability of occurring, and each trial is independent of all others. In other words, if we roll a die, the first time we roll it, the probability of getting a 3 is going to be 1/6. And then if we do it again, the probability of getting a 3 is still 1/6, and so on. Now, what is a binomial experiment? A binomial experiment is created when an experiment contains multiple Bernoulli trials. So if we do those trials I just mentioned multiple times, then that makes it a binomial experiment. You can read here, I give a little blurb here about where the name comes from, but I'm not going to focus too much on that. Alright, so experiment 1. Let's say flipping two coins, and we're going to do it 3 times, and we're going to say success is getting ahead. Now right now I'm not solving a problem, I'm just giving you the values for P and Q. So the coins being the same, there's 2 out of 4 ways they can be the same, so that probability would be 1/2. And then, so 1 minus 1/2 would be the probability of the coins not the same, because those are the only two things that can happen if I break it down like that. Let's say we roll a die 10 times, and success would be rolling a 3. Well, then probability of success would be 1/6, and the probability of failure would be 1 minus 1/6, which is 5/6. Let's say a basketball player has a 72% free throw shooting average, or whatever the shot is. Yeah, free throw. So if success is making the shot, then the probability of success is 0.72, and the probability of failure would be 1 minus 0.72. Suppose you guess on a multiple choice question. Then your probability of success on a question would be 1/4, and the probability of failure on each question would be 3/4. You might select an item from a group that has 7 good items and 3 defective items. And let's say you do that multiple times. Well, the probability of success on each trial would be 3 out of 10, and the probability of failure would be 7 out of 10. Notice this time I said success would be selecting a defective item. Let's say you try a new medicine out on 20 people, with the success being the symptom is eliminated. Okay, so if the company has figured out that they get an 80% success rate, then the probability of success would be 0.8 and on a particular trial, and success would be 1 minus 0.8, which is 0.2. If you plant 3 tulip bulbs that advertise a 90% maturity rate, let success be that a tulip matures, then the probability of success would be 0.9, and the probability of failure would be 1 minus 0.9, which is 0.1. Now, this part right here talks about how to develop the binomial formula. And so you can slowly scroll through the video, freeze it a time or two, and read this if you like. But it just sort of gives you an idea of why we have the calculations are calculated the way they are. So for example, on the tulips, if you get no successes, the probability of no successes would be that you can say 0.9, that's probability of success to the 0 power for no successes. But if you have no successes, then all 3 failed. So you could say 0.1 times 0.1 times 0.1, which is 1 cubed. Now, the 1 is because there's only one way that you can get no successes. Now, I'll explain that here. This will make more sense. Suppose you only want 1 success. Okay, so if you only want 1 success, then we would say 0.9 for the 1 success times 0.1 times 0.1 for the 2 failures. But there's actually 3 ways that can happen, so we multiply it by 3. And the reason is because the first plant could mature, or the second plant could mature, or the third plant could mature. So for each way to get 1 success, there's 3 ways it can happen. And then the same thing is true for 2 successes. For 2 successes, you could have the first 2 mature, the first and last mature, or the last 2 mature. So that's 3 ways to get 2 successes. But for 2 successes, that would mean you have 0.9 times 0.9 for the 2 successes, then 0.1 for the 1 failure. And then to get 3 successes, there's only one way that can happen, and that's if all 3 mature. And so that would be 0.9 times 0.9 times 0.9, and that should be a 1. Sorry about that. And that's times 1, and that's 0.1 to the 0 power. Okay, so if you'll notice, 1, 3, 3, 1, those 4 coefficients are actually the same coefficients you would get if you cubed a binomial. And that's all I'll say about that. Okay, now notice there's a pattern here. The first one, for 0, you had a coefficient of 1. Well, that's the same as 3 choose 0. The second one, you had a coefficient of 3. Well, that's the same as 3 choose 1. The third one was also a coefficient of 3. Well, that's 3 choose 2. And then the last one was a coefficient of 1, which happens to be 3 choose 3. And then notice the powers of 9 go up as you get more successes, and the powers of 0.1 go down as you get more successes. Well, actually, the probability of X successes in a binomial experiment is this formula. N, choose X, where N is the total number of trials, X is the number of successes you're looking for. You take P raised to the success, and then Q raised to N minus the number of successes. So for instance here, for 2 successes and 1 failure, X is 2. And since X and N is actually 3 because I have 3 trials, I mean, sorry, not 3 trials. Well, it is 3 trials, but it's 3 plants. So the probability X is 2 would be 3 choose 2, and then the probability of success to the second power, and then the probability of failure to the first power, and you can think of the first power as 3 minus 2. So each of these can be calculated with this formula. Now, let's take a look at an example here. Suppose 60% of mothers prefer toothpaste brand A above all others. Let's say a sample of 10 mothers is selected. So basically we're saying the probability that a mother chooses brand A is 0.6 and the probability she doesn't choose brand A is 0.4. So let's find the probability that exactly 5 mothers prefer brand A. Now N is 10 here because I have 10 mothers, so that's like 10 trials. And P is 0.6 and Q is 0.4. The probability that exactly 5 would be, probability X equal 5 would be 10 choose 5 times P, which is 0.6 to the 5th, and then times Q, which is 0.4 to the 5th, and you get 0.201. Now, what about that 5 to 7 mothers prefer? Well, for 5 to 7, we'd have to find the probability of 5 mothers, and the probability of 6 mothers preferring it, and the probability of 7 mothers preferring it. So for 5 mothers, we just did that. For 6 mothers, that would be 10 choose 6 times 0.6 to the 6 and 0.4 to the 4. And then for 7 mothers, it would be 10 choose 7 times 0.6 to the 7 and 0.4 to the 3rd power. And then you would add each of these probabilities together, and that would give you the probability that 5 or 6 or 7 mothers prefer brand A. How about more than 80%? Well, more than 80% of 10 mothers would be 9 mothers or 10 mothers. So we have to find the probability that 9 mothers prefer brand A, and that would be 10 choose 9 times the probability P to the 9th times probability Q to the 1st. And then we have to find the probability that all 10 mothers prefer it. So that would be 10 choose 10 times 0.6 to the 10 times 0.4 to the 0. And you add those two numbers together to get your final answer. And then if you want fewer than, fewer than 9 mothers, the easiest way to do that, if you want fewer than 9 mothers prefer brand A, you want the probability that the number of mothers that prefer brand A is less than 9. So what you can do, since you know the probability of 1 through 10 must add up to 1, then take 1 minus the probability that X is 9 or 10. So up here, I did 9 or 10, and I got 0.04636. So I can just subtract that from 1, and now I know the probability that X is less than 9. And then you can do a similar thing for at least 1 mother. For the probability of at least 1, then the complement of at least 1 would be 0. So find the probability that 0 mothers prefer brand A, which is actually about 0.0001, and you get 0.9999. So that's how you would do something like that. Now I'm going to scroll through slowly through these examples, and then you can freeze the video and look at them for yourself. Okay, so here's 4 problems. Freeze the video and take a look at them, and notice that the problems are on the left and the solutions are on the right. And hopefully from my lecture you can tell how I solved each of these questions. So freeze the video and look them over real good. Work them yourself if you like. And then I'm going to move on to the next couple of problems. I want to wrap this up with the formulas for the mean and standard deviation of a binomial experiment. To find the mean of a binomial experiment, you just take N times P, and the formula is down here. So N times P is the formula for the mean. And then for standard deviation, you just take the square root of NPQ. Freeze the video if you need to, and then look at the rest of the problems.